Hello everyone, welcome to Astronomy 405, and today we're moving out of talking about planets and moving to talking more about some of the many other things in our solar system that are not planets, or not even close. So that's right, we're talking about small bodies. So we're going to give an overview of classification and talking about how we study them as a population, and then the next lecture will be about individual composition and that kind of stuff. All right, so what are we doing today? We're talking about classifying small bodies by how they orbit, which will also cover where small bodies orbit, which is pretty much everywhere. And then distinguishing between two kind of big classes of bodies, comets and asteroids and other asteroid-like things. We're going to just call them minor planets. And we're also going to start talking about size distributions. So I found this picture to try to explain why this is such a complicated and annoying problem, which is, originally you might think by things like size and clearing orbit, the International Astronomical Unit defined. You had planets, which were round and cleared their orbit, dwarf planets, which are not clearing their orbit but are still round, and small solar system bodies, which are neither round nor have they cleared their orbit. But you also have some differences. For instance, a comet regularly gets close enough that it starts vaporizing, and that might be different than other bodies that don't. Even then, there's degrees of comethood. The composition of something in the main belt might not be the same as the composition of something out past Pluto. What we're going to do is talk a little bit about how we classify things by orbit, and the next time we'll talk about compositional stuff. Some useful terms. A major planet is, again, the hydrostatic equilibrium. It's round. It's cleared its orbit. It doesn't live in an asteroid belt, and if it was put in an asteroid belt, you would, within the age of the solar system, no longer have an asteroid belt. Dwarf planets are round, but they haven't cleared their orbit. And small solar system bodies are neither round nor have they cleared their orbit. So basically everything that orbits the sun and is a natural body falls into these categories. So let's talk a little bit about small objects and other classes. So one is that we tend to divide things into comets and asteroids and things that are like asteroids, which we call minor planets. So comets, we had a definition of comets pre-telescope because they were some of the things in the solar system we could actually see. Comets generally are classified by, if we see outgassing as this object orbits the sun, then we call it a comet. If we don't, it's a minor planet. Now that's actually a pretty fuzzy definition, because there have been objects we found that were later reclassified as from one to the other because we found outgassing. Now, generally speaking, the minor planets that orbit interior to Jupiter, we call them asteroids. In fact, we might even include the Trojan asteroids, the ones that orbit, in or near Jupiter's orbit, in this category. Now, past Jupiter, we tend not to call those objects asteroid, even though they are in the same classification system. They're minor planets. They generally get classified by where they orbit. Some folks tried to get asteroids going, but asteroids didn't happen. Now, comets also get a classification system based on how they orbit, which is mostly do they come back. Short period comets have orbital periods of about less than 200 years. That usually means that the farthest they might get out is the giant planets or the Kuiper belt. So we've seen them regularly, and they also tend to have low orbital inclinations. They are prograde comets. They have orbital inclinations that are not dissimilar from minor planets. And we think that they tend to come from the Kuiper belt. They look a lot like what happened if you kicked a Kuiper belt object inward. Long period comets, those have orbits that are very close to parabolic. They come in essentially at random orientations. They have all inclinations, including retrograde ones. And their orbital periods tend to be thousands of years, and they tend to be pretty poorly defined because they are not very strongly attached to our solar system. We think these come from the Oort cloud, which is mainly defined by a little bit of theoretical modeling of solar system formation, and a lot of observation of these comets have to come from somewhere because comets outgas. That means eventually they go away. So a little bit on naming minor planets. So whenever you discover something, a minor planet or a comet, it gets a temporary designation. And the two have slightly different designations for historical reasons. For instance, I have this object that I picked out at random, 2003 VB12. 2003 basically means it was found in 2003. Or rather, it was observed, or rather the orbit, it was first reported in 2003 and the orbit was calculated. There might be what are called precovery pictures, which are pictures that are, which is that astronomers, once we knew its orbit, we went back and looked for it in other data before we identified it. Now, the letters, the next bit is telling us kind of just a basic method of listing what objects are found. V means it was found in the first half of November. How it works is each half month gets a letter. And the first object in that list will be, first object found in the first half of November will be VA1. And then the second letter basically groups things in 25s. So you get VA, VB, it's the next one, not VB12, just VB, VC, etc. And 25 letters are used. I believe I is also skipped because I is an ambiguous letter. And the final number is because we've had to cycle. Originally people didn't report 25 asteroids in the same 2 weeks. But now we find scads of the things. So the 12 is telling us how many times have we gone through this cycle. So 12 times 25 is 300. So we gone through this cycle 25 times. And then now we're doing B again. So it's the 12th time it's the 12th 2003 VB object. Now, once you confirm this thing has existed, the temporary name is when you say, hey, I found this thing, let's try to get a good orbit for it, and confirm it's actually an asteroid or something. Then it gets an official number in the minor planet catalog. So basically we identify it is a minor planet, it gets a number that is based on what order it was reported. Minor planets may be named. Not all of them are. You can see there's lots of them. For instance, 2003 VB12 was given the number 90,377. So at that time, and we are now into the 6 digits. So usually what happens is if they're particularly interesting or are just, an astronomer wants to, honor people, they are given, an object is given a permanent name. So in particular, this object is particularly interesting, so it was given a name. It's now called 90377 Sedna, or just Sedna for short. Now, there's often a recommended theme, like Kuiper Belt objects are often named after, especially big Kuiper Belt objects are often named after deities associated with creation. But other objects, especially ones we found lots of, just have a few prohibitions. For instance, if you find a main belt asteroid, you can't name it after yourself. You can't name it after a current political figure or one who's less than 50 years dead. And, you have to give it a relatively serious and, serious name. Now, do interesting exception in that there's been enough asteroids that people have started naming them after their friends and colleagues, and if they can show they're interesting people who have a connection to science, and even like some science fair winners. For instance, there's an asteroid named after a science fair winner, Alexandria Ocasio-Cortez. Now she's a political figure. She's a representative in the House of Representatives from New York, but she was in high school when the asteroid was named after her. So she is the only political figure. So she accidentally found the loophole. You're allowed to name asteroids after political figures if they're not political figures when they're named. They're science adjacent people. All right. Comets, on the other hand, comets you can name after yourself. That's the tradition. Whoever finds the comet gets their name attached to it. So comets also get a kind of a lettering system. So they have their year, and then they have a number, or letter, and a number to tell you what order they found it. But there's a number of interesting classes of comets that we find, which is, so that's also included in the name. In the P comets are periodic. Those are the ones that we've seen more than once. Or if we find a comet and we know it's on a short period orbit, we're going to see it again in under 2 centuries, it'll often get a P on its discovery. C is for comet, is for the non-periodic comets. Those are the ones we see that are long period. We don't, their orbits are not well bound to the solar system. They may or may not come back. X is for historical comets that we don't have a good orbit for, so even if they did come back, we wouldn't find them. D is for comets that are lost or destroyed. For instance, D93F2 Shoemaker-Levy 9 crashed into Jupiter. But you can also have comets that break apart. And I, which is a newer category, we've only got 2 objects in it. I is for interstellar objects. For instance, I 2017 U1 is Oumuamua, the first interstellar object we discovered. It went through several different classifications. Technically, it's not really a comet. It doesn't outgas, but it's still kind of on the list as is mistaken for a comet. We've only got 2 objects in this list, Oumuamua and comet Borisov, which is a comet. It looks very, very normal for a comet, except it's coming in at well past escape speed. All right, so let's talk about where we find minor planets. First, we have 3 belts. The main belt, it's between Mars and Jupiter. We often call those objects main belt asteroids, MBAs, not to be confused with the degree the business college gives you. Kuiper belts, that's out past Neptune. There's a nice belt there. Objects are KBOs, Kuiper belt objects. The Oort cloud is way, 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 way past Neptune. Unlike the belts, which are mostly pretty flat, objects don't have inclinations of a few tens of degrees at most. The Oort cloud is a cloud. Everything has random inclinations. And again, we don't see that directly. Now, some other common objects we're going to talk about are near-Earth objects. These are objects that are between Mars's orbit and the sun. Centaurs, those orbit, so near-Earth objects orbit kind of within the inner planet zone. Centaurs orbit between Jupiter and Neptune. So they're in between the main belt and the Kuiper belt. Trojans are exempted from near-Earth objects and centaurs because while they orbit in the zones where planets live, they are trapped in the planet's Lagrange points. There's also a little bit more classification out past Neptune that we'll go into. The general term for objects past Neptune is trans-Neptunian objects, TNOs. There's a lot of 3-letter acronyms in this. All right, so let's look at the belts first. The main belt has about 4% of the mass of the moon in terms of rock. And most of that mass is in the handful of large objects, including the dwarf planet series. Now, you can see it's more eccentric than all of planets except for Mercury. The average eccentricity of asteroids is quite large compared to the big planets, and as is the inclination. In this picture, the green objects and the kind of gold objects labeled Hildas are main belt objects. The Hildas in particular are quite unusual. You can see they're the ones that tend to live in the outer reaches of the belt, and they are in a resonance with Jupiter. Now, what shapes the main belt? So the bottom plot is a plot of semi-major axis versus number. And you can see it kind of divides based on the colors. It divides into 3 regions. It's not apparent when you just plot the positions like we did on the top. Because, again, eccentricity and inclination means that asteroids are crossing those distances all the time. It's just that asteroids don't have average distances at those distances. And these are resonances with Jupiter. So we talked about resonances way back in the beginning of the term. So 3 to 1. That means the asteroid orbits 3 times, Jupiter orbits 1. Jupiter kicks it out. 5 to 2. The asteroid orbits 5 times, Jupiter orbits twice. Jupiter tends to kick those out. 2 to 1 kind of marks the really outer edge of the asteroid belt. Again, asteroid orbit twice, Jupiter orbits once. There's a few objects out past there, and the Hildas are in a protected resonance. They're in the 3 to 2 resonance. They orbit 3 times for every 2 times Jupiter does. The inner edge is a little weirder. It's shaped by not an exact resonance with Jupiter, but one of those secular resonances. And again, we talked about this way in the beginning of the term. Okay, now let's talk about near-Earth objects. Now let's talk about near-Earth objects. Individual objects don't tend to hang around this area as long, but there's a constant influx. If an asteroid gets pushed into one of those resonances, it's possible it'll end up on a near-Earth orbit. Similarly, if you have a comet, and the comet stops being a comet, it's run out of stuff to outgas, it's now a near-Earth asteroid. Our official definition is, if an object comes within 1.3 AU of the sun, it's a near-Earth object. Most things don't go back to the main belt. Some of those extinct comets might. Now, we know of about 22,000 near-Earth objects, and I had to update this slide because the slide said from 2 years ago we knew about 17,000 near-Earth objects. Now, the change from the large ones is much smaller. It went from about, I added about a dozen objects over the last 2 years. And we also classify these by orbits. So we look at the pericenter distance, the apocenter distance, and the semi-major axis. So Amora asteroids never cross Earth's orbit. They are near Earth objects, but they always stay outside of Earth's orbit. And they're named after the first asteroid discovered in this group. Apollo astronauts do cross Earth's orbit, but they have a distance larger than 1 AU. A-10 asteroids have a distance smaller than 1 AU. Ooh, that's an error on the slide. But they still cross Earth's orbit. And there's another class of objects that never come outside. They never go outside Earth's orbit. They're always inside Earth's orbit. And they have 2 different names, Apohele and Atira. Atira is the prototypical object. Apohele comes from a Hawaiian word for orbit. So here's the kind of way to think about it. How much object time do these objects spend outside of Earth's orbit? Your Earth is in blue. We have the 3 more well-known classes. And again, Atira objects are not plotted. So Amora asteroids are always outside the Earth's orbit. Apollo spends most of their time outside the Earth's orbit, but not all. A-10 spends some of their time outside the Earth's orbit, but most of the time inside. And Atira never gets outside Earth's orbit. Here are some discovery statistics from 2018 for near-Earth objects. And I do include comets. And you can see most of the objects we know about are Apollo and Amor. Only about 8% of the objects we have are A-10 or Atira. And the reason is because it's hard to discover stuff that mostly lurks within our orbit. It's always going to be close to the sun in our sky, which makes it hard to find. So there is a distinct observer's bias, and it's also why astronomers are really interested in finding this stuff. That's also why we have so few Atira objects, because A-10 objects, occasionally they do pass outside our orbit, so they would be visible again far from the sun. far from the sun in our sky. So, all right, that's near Earth. Let's go outward. Jupiter has a bunch of objects in its Lagrange point, and these might be as much as the main belt. We are preparing a spacecraft called Lucy to go out and visit the Trojan asteroids. Now, they were originally named because while most of the original main belt asteroids were named after women from mythology, the first few were Ceres, Pallas, named after Pallas Athena, Vesta, and Juno, all goddesses from Roman and Greek mythology. The Trojans were named after characters from the Trojan War. In particular, most of them were divided into two camps. So they named nearly all the asteroids in the Greek cloud are named after Greeks. Nearly all the asteroids in the Trojan cloud are named after Trojans. So you have lots of names from the Iliad, so lots of good asteroid names. But these may be as numerous as the main belt. We don't see as many because they're farther away. Neptune also has a lot of Trojans, which makes sense. It's another big planet near an asteroid belt. The other planets have few to none. Earth does have one. It does not have it has a temporary name. Mars has a few, and any others have few to none. So let's look at the trans-Neptunian objects. We'll come back to the centaurs. So trans-Neptunian object, that's the word for anything past Neptune. Now, many of those live in the Kuiper belt, which is a belt of objects that lives past Neptune. This plot is showing the distance in astronomical units, A, you can see that plotted at the top, and the inclination of the orbits in degrees and they're color-coded by what sort of objects they are. The Kuiper belt are the red and the blue objects. And there are a few different classes of those. So the Kuiper belt has a lot more stuff than the main asteroid belt. It might have as much as 1/10 the Earth's mass. And we have several dwarf planets that live there. Now, the inner edge isn't exact, but the 2 to 3 Neptune resonance seems to be a good place to mark it because there's a lot of stuff there, most of it trapped in that resonance. That's also where you find Pluto, the largest object in the Kuiper belt that we know about. And it goes out to the 1 to 2 resonance, the Kuiper cliff. And why there's a cliff there, we understand why there's a gap there. Just like in the main belt, we would expect a gap there. But we don't know why the Kuiper belt doesn't pick up after that. It is an unsolved problem in astronomy. Now, classical Kuiper belt objects, which are sometimes called cubanos, because they are after the temporary name of one of the first discovered objects. The second Kuiper discovered object was QB10, was its temporary name. You don't hear that as much. You normally hear Kuiper belt objects. Now, these are in orbits that stay far enough out of Neptune's region of influence that they're not being pushed around by Neptune. And there seem to be two groups. I'm going to go back a few slides. There seem to be two groups of Kuiper belt objects. We have the cold group, which is kind of clustered at the bottom there. These objects have pretty small inclinations and eccentricities. And you have the hot group near the top. Those have larger eccentricities and inclinations. Now, when we're talking cold and hot, this is a dynamical term. So you imagine a gas, the particle, if the gas is cold, the particles are all moving their random velocities are relatively slow. If the gas is hot, they have high random velocities. When we say cold and hot in dynamics, that's talking about those random velocities. Cold objects, dynamically cold objects, have low eccentricity and low inclination because they're just kind of nicely circling the sun. They have the systematic motion, but they don't have much random motion compared to other cold objects. Hot objects have higher inclinations and higher eccentricities, so they have more random velocity. And the interesting thing about this is they seem to be two different populations. that in general, cold classical Kuiper belt objects tend to be redder than the hot classicals. They're going to be brighter. They tend to have a higher albedo. That's what I mean by brighter than the hot classicals. They're more likely to have binaries. And there's many fewer large objects. The two dwarf planets we consider classical Kuiper belt objects, Haumea and Makemake, are both dynamically hot objects. Haumea is kind of an ambiguous whether it's a classical Kuiper belt object or not. It's got one of the examples of the cold objects is the second object New Horizons visited, Arrokoth. It is, which we'll talk about later. Now, the other thing that's in the Kuiper belt object are the ones in Neptune resonances. Pluto is the largest and most famous example. Pluto is in a 2 to 3 resonance with Neptune. You can Orcus is another big example. You can see Orcus and its moon nearby, in the kind of scale picture. Orcus is also in the 2 to 3 Neptune resonance. And one informal name for these are Plutinos. In fact, to the point where someone suggested that the ones in the 2 to 1 resonance, which you can see also in green, are at the, again, other side of the Kuiper belt. You can see also in red, have the other side of the Kuiper belt, suggested that those objects should be called Tutinos. Now, everything in the Kuiper belt is in a controlled relationship with Neptune. Either they never get close to Neptune, they're practicing good social distancing, or they only see Neptune at regular intervals, so their interaction is very controlled. Scattered disk objects are stuff out past Neptune that aren't in nice controlled interactions with Neptune. So they are going to get close to Neptune eventually and get pushed around. Now, usually they're farther out than the Kuiper belt, but they have large eccentricities and also large inclinations, so they can get to 30 AU where Neptune is on a nice circular orbit. Eris is an example of this. Eris is an example of this. These are harder to find because they're farther out. The farther you go out in the solar system, the harder it is to identify these objects. And there's also a lot fewer of them. So, all right, just like we have near-Earth asteroids that are objects that used to be in the main belt, got kicked out, and now are orbit among the planets until they eventually either hit something or fall on the sun, centaurs are the equivalent from among the giant planets. They were so named because the first one we found was called Chiron, after a mythological centaur. Now we have a theme. So basically, the rule is if their semi-major axis is between Jupiter's and Neptune's, they're a centaur. Some of these are also classified as comets because classifying objects is not an exact science. Not everything fits in a neat box. Some of these objects get close enough to the sun, they form a little coma, a little outgassed cloud. Now, there is some debate about what exactly counts as a centaur versus a scattered disk object, because there's a few centaurs whose orbits extend past Neptune's orbit. So that technically kind of puts them in the scattered disk. We could just say, well, maybe centaurs are Kuiper belt objects that were scattered inward and scattered disk is outward, but it seems possible that Neptune could make an object go from one to the other. Now, there's a few objects that are really puzzling to us because they are really out there, and unlike the scattered disk objects, which orbits can get close to Neptune, which means that the reason they have such weird orbits is probably just Neptune messing with them, there's objects that don't seem to be interacting with anything much. And they're not on nice circular orbits, so something had to push them out there, but they don't seem to be near anything that could have done the job. Yeah, so they're puzzling. We call these detached objects, and one of the largest is Sedna. So objects on Sedna-like orbits are often called sednoids. Again, it's when in doubt, if you're an astronomer, name it after the first one you find. You can see we changed the scale here. Now the Kuiper belt is much, much narrower. We're going out to hundreds of astronomical units. So you can see the scattered disk in kind of gray, kind of peters out. The objects discovered out there are more eccentric, because remember, scattered disk objects have to interact with Neptune. But in white, we have our detached objects, including Sedna. This is one of the things that gives fuel for the idea that there's a planet lurking out past Neptune, because that would be one explanation for how you could get a Sedna. Now, let's talk about the Oort cloud. So in the middle of the 20th century, Jan Oort was considering long period comets, and he noticed they all seemed to come in from basically infinity, from essentially nearly outside the solar system. And he started trying to do the math, both about, okay, we know comets vaporize. They're not gonna, they can only make so many passes close to the sun before they either totally vaporize, they stop, they run out of gas near the surface, so they become essentially an asteroid, they break apart, all kinds of stuff. So based on the rate of comet discovery, he estimated how many comets there had to be and how many comets there had to have been over the history of the solar system. He estimated, well, if we're seeing these rates, there must be, trillions of those things out there. And they all seem to be coming from a zone that's 50,000 to 150,000 AU from the sun. And this is the table from his paper. And because of how he fit orbits, it turns out 1 over A is easier to fit than A. So he was noticing that it definitely seemed to be coming from really far away. And they saw less they were coming from only mostly far away. Now, based on those comets, we know the Oort cloud is a cloud, not a disk. The long period comets we see come at us from all directions. Half of them are orbit retrograde, half of them orbit backwards. And we have never seen the Oort cloud directly. We only know it's there because we keep getting these comets from it. Compare Sedna. Sedna's semi-major axis about 500 AU. And we think the Oort cloud, at least the part of it that sends comets at us, extends out to 50,000. There's some thought that there might be an inner part of the Oort cloud where the comets are a little more firmly attached. We don't often see stuff from them. We don't often get them knocked into the solar system, which is even harder to see because we're not even getting those. Okay, so that is the populations of objects. We talked about near Earth, main belt, centaurs, the Kuiper belt, which we divided into cold classical, hot classical, and resonant, the scattered disk, and the Oort cloud. And we also mentioned Trojan asteroids. All those have basically dynamical definitions. Oh, and the detached objects like Sedna. Nearly forgot about those. So now let's talk about how do you study something where there's thousands of the things. Now, that's kind of in contrast to planets. Planets, we can study Mars in depth because there is only one of Mars. There's only one Venus. It makes it hard to do comparative science, but easy to say we have a general idea about what Mars is like. And you can we've done this with the bigger objects we've done this with dwarf planets and some asteroids. But we also want to get an idea of statistics. We also want to consider, how do we study something, we also want to get used to the idea of studying this as a population rather than just as a collection of individual objects. So one way we can do this is talk about a size distribution. This is also useful because I've told you how much mass is in the asteroid belt and the Kuiper belt and how many Trojan asteroids Jupiter has. And the problem with estimating that mass is, again, there's a lot more small stuff than big stuff. There's 8 planets and probably dozens of dwarf planets. And scads and scads, millions of small solar system objects, just, maybe even more, just depending on where you draw the line before I'm going to stop counting. So what we can do when we have scads of objects is we can start putting together a distribution of properties like size. So we can fit a function to this. So let's say we want to figure out how many asteroids are in a given size bin from some R min to R max. Now, we're going to expect a lot more closer to R min than R max. That's just the way the solar system works. And what we can eventually do is come up with a function that tells us how many asteroids are in each tiny infinitesimal size bin, dr. And because we don't always have a good sampling, one of the first things astronomers will do will fit a power law to it. That is some function that is ax to the b. So down here you can see our power law. The front number outside the parentheses is basically a normalization constant. You want, that tells you how many asteroids you have in general. And then the thing in the parentheses is our variable r. It's usually scaled by some reference radius r naught. And the little Greek letter is then telling us what's called the power law index. It's telling us how steep it is. Now sometimes you'll see this written as negative power, like negative rather than just positive, because it's usually a negative power law. It's usually there's more small stuff than big stuff as r increases and decreases. So you can integrate this to figure out how many number of objects are per radius bin. You can also do things like, well, let's assume the mass is correlated with r cubed. Seems a reasonable assumption. Then we can add a 4/3 pi rho r cubed and find the mass distribution function. How much mass is in each radius size bin? Sometimes we might want to find surface area distribution function. I do that a lot with Saturn's rings, in which case we need 4 pi r squared. Now this is just kind of our nice generic, we're not going to overfit it type of function. So even if we don't have a good understanding of the details of the actual distribution, this will give us a few numbers we can compare populations. And it usually does a decent job. Now the other function I have here, n greater than, is the function of is the number of objects larger than r radius r. So basically what we just did was integrate from radius r to positive infinity. And we get this function that looks like that. Now how this looks is, this is a plot of the cumulative number of asteroids bigger than d versus d, and these are all models. Each team gets a different symbol, and they're not all perfect power laws. You can see there's some bumps and wiggles based on real observations of asteroids. We have a much better idea of how many asteroids there are that are 1,000 kilometers or 100 kilometers than we do of asteroids that are 10 meters. But you can see on a log-log scale, a power law looks like a straight line. This is also pretty handy for asteroids because it means that you can measure the deviations from the straight line and focus on that, kind of take off the straight line that pretty much every power or any size distribution in the solar system will have that average. There's more small stuff than big stuff. But you can take that off and study those bumps and wiggles without. Now what we can learn from this? Well, collisions tend to produce a size distribution that's about -3.5. And that's if only the object speed and the object size ratio matter. So if you have a population that is, its size distribution only depends on, on the collisions, you would expect to measure a power law of -3.5. If you measure something different, that indicates other stuff is going on. So for instance, asteroids and trans-Neptunian objects seem to have a population close to this power law index. Comets don't, though. The comets we see do not seem to be this, which kind of makes sense because comets are outgassing. They're changing their size. Now, I have a particular interest because my dissertation and the work I'm trying to finally get published is on the size distribution of Saturn's rings varying from place to place. It only gets to about 3.5 in a few places. So, all right, let's talk about collisions. Since I've mentioned them, I've said that the sizes of asteroids is mostly shaped by the fact they're hitting one another. How do we study that? And one way you study that is to look for asteroids that have similar orbits. Now, one of the problems is that Jupiter is shoving, well, Jupiter can't shove a non-resonant asteroid too hard. You know, Jupiter is, remember, resonances allow Jupiter to basically build up a large unidirectional one direction shove. Most of the asteroids in the asteroid belt, Jupiter just kind of encounters at random phases of their orbit, so it just gives them a push and they essentially have a random walk of their orbital elements due to Jupiter. That means if you plot their asteroid orbital elements, you get something like on the left. That's asteroid eccentricity versus inclination. You know, you can draw some general conclusions about the population, like, hey, there's fewer asteroids at higher inclination and eccentricity. There's few asteroids at 0. Not terrible, you know, there's some blobs you can kind of try to pick out, but it's not too interesting. But if you average over long periods of time, basically to eliminate the perturbations from Jupiter, you get what are called proper orbital elements. Previously, the one on the left is what's called osculating orbital elements. This is the asteroid's orbital, you fit an orbit to this asteroid at a given time. Proper orbital elements adjust for perturbations from like Jupiter, since we know Jupiter is there. And there, the plot makes a lot more sense. We see it's a lot clumpier. And those clumps are basically what we think of as collisional families. Those are families of asteroids that used to be one big asteroid, or maybe a few big asteroids, that were broken apart, and now the objects have slightly wandered a bit in their orbits, but not that much, ignoring what Jupiter's doing to them. So we can start to pick out asteroid families and use that to study how objects have changed. So for instance, Vesta is the second largest asteroid, and didn't bring a picture of it, but it's got 2 big holes in it, 2 big craters. So it makes sense it's been whacked around a bit. So we can try to pick out what objects are in Vesta's family, what objects we might expect to look like Vesta, to study what happened, how much stuff that was knocked off Vesta. So you can see the top plot is the whole asteroid belt, and we're plotting this time A versus I. And then you can see the Vesta family. And the second plot says, okay, well, we're going to ignore everything past 2.5 and just plot E versus I. It gives us a little more clean picture. See that the eccentricity lets us separate out another asteroid family, the Flora family. And then what astronomers do is they try to identify which objects are probably in the family, like in this case, they get red circles, which objects are in the family, but they're kind of at the outskirts, so they might not be real members, the purple circles, and then which objects are just random asteroids that happen to coincidentally have the same kind of orbit as family members, and those are called interloopers. You can see there's a few there. Asteroids collide a lot, and it changes how they look. So here are some small asteroids. This is 25143 Itokawa and 101955 Bennu. You can see they're less than 1 kilometer in size, and these asteroids are smashed all to heck. Non-technical term. Bennu is currently being visited by the OSIRIS-REx spacecraft, which is going to bring us back a piece of it, which will help us study it. So we call these kind of objects rubble piles because basically the number of collisions they've undergone has basically completely pulverized them, and they're held together by their kind of weak gravity and maybe a few large pieces like Itokawa. Itokawa is mostly shaped by a few large pieces. Bennu is vaguely spherical just because it's not got very much internal strength, so it kind of forms just basically due to its very tiny gravity. Now rubble piles are pretty, on the one hand, they're like hitting sand. They dissipate impact energy pretty well. That's one reason why they don't really have craters. But if you smack it hard enough, you can send them flying because they don't have very much material strength. They're held together by very, very weak gravity. In fact, you can talk about some of those non-gravitational forces, again, way back in the beginning, like the Yorp effect can spin these things up enough that they start launching material. In fact, you could see stuff kind of coming off Bennu. Get to bigger asteroids like Ida or 243 Ida or 21 Lutetia, and they look a little bit more shaped by impacts and random material forces. They're not round like Ceres or Pluto, which are hundreds or thousands of kilometers across, but they clearly are partially to mostly solid, which is why they can hold on to craters. Now, the other thing you might have noticed in this picture is Ida has a moon off to the right. That moon is Dactyl. Ida was one of the first asteroids we flew by. It was flown by the Galileo spacecraft on its way to Jupiter. It's passing close to Ida, so the mission directors noticed this and decided, hey, we can tweak its orbit a bit and we'll fly by Ida. They also flew by an asteroid called Gaspra. So Ida has a moon. And I've mentioned satellites before. I've mentioned binary asteroids before. Ida's moon, Dactyl, was the first one found. And they're hard to see. You know, asteroids are not big and their moons tend to be smaller. Where we often see them is in radar. When a near-Earth object flies by the Earth, we can send out some radar and basically get a kind of very odd picture of it. There's some radar pictures below, and what they tend to do is they plot what are called delayed Doppler images. They plot the time it takes the radio waves to go the distance and get back, that's the delay. And the Doppler shift when they cut back after being reflected off the asteroid, that's the Doppler. That's why the moons kind of have those little smeared out along their orbits. Now, we also can find a few in telescopes, especially the big objects. And the interesting thing is 2% of asteroids have satellites. They seem to be slightly more common in near-Earth objects, which, if they're created by the asteroid spinning up and launching stuff from the surface due to the York effect, makes sense that we'd expect to find them in regions where sunlight is stronger. Trans-Neptunian objects are different than the main belt, though. 11% of trans-Neptunian objects have satellites. And keep in mind, we're only looking at the big ones. We can't see a lot of the small trans-Neptunian objects, but we still, even among the big ones, most of them have satellites. Pluto is not an outlier here. In particular, all of the confirmed dwarf planets have at least one moon. Pluto has 5. This is a Hubble picture of Pluto and Charon, and then the image Pluto and Charon were blocked to get rid of their brightness, so we could find 4 other moons: Styx, Nix, Erebos, and Hydra. And then the bottom is the New Horizons pictures, roughly to scale. We didn't get very close to Styx or Erebos. You can see that those are bitty moons, while Charon is a lot more like a lot more like a tiny dwarf planet. Now, what we also have are contact binaries like Arrokoth. Arrokoth was the other object New Horizons flew by, and it's only a few tens of kilometers across. We did find it from Earth, but it did require a dedicated search. Now, what Arrokoth is we think it used to be 2 objects that slowly spiraled in together to form one. And the cold classical Kuiper belt often seems to form these things. So that's some big clue of how we think the solar system formed. We're going to talk about that when we get to the last week of class. We haven't found any centaurs with moons, but two of the large ones, Chariklo and Chiron, have rings, and the rings are pretty narrow. And on gas giants, often narrow rings mean moons are kind of confining them. So we don't have any evidence for sure. This is an attempt to look at Chariklo's rings by stellar occultation, measuring the light of a star as it passes behind Chariklo as seen from Earth, and Chariklo's rings. So what we talked about today, we talked about all these classification systems. There's a lot of it. Now, the other thing is we said the distinction of comets, as comets have the gas around them, they have a coma, or at least they get a coma at least during part of their orbit. Minor planets don't. We often study objects by their size distribution. And the other thing we have to worry about is moons, satellites. Next time, we're going to look at, roughly speaking, what is the composition of asteroids and what is the comet? What is the composition of comets? And how do we know?